in this lecture we started with turbulent flows, okay, and we said a few things about turbulent flows, and the first point that we mentioned about turbulent flow is that energy is cascaded and never accumulated. This is one of the most important thing, and of course, the dependence on initial conditions and boundary conditions. This I explained by giving you the example that if you take the same measurement at the same time instant even for a pipe flow, you will find that the velocity profiles will come out to be very different, whereas the statistics, that is the first moment and the second moments, those will match. So, no matter how good your experiment is or how good your simulation is, it is always the nature of turbulence is to amplify those minute differences, okay, so that you get very widely different profiles, okay, in the temporal space. Okay. So, but the important part was we also said that the energy is always cascaded and it is never accumulated. That means, from the large eddies you get the energy which is transferred to the smallest eddies, where viscosity becomes important and viscosity actually dissipates the energy in the system, right. So, the energy per unit mass okay, it can be given as u square, which is that is at the highest, that is at the largest eddy level, is u square divided by L by u, where this L by u is basically called the eddy turnover time. It is basically the time that it takes for an eddy to rotate, okay, to break or to rotate. So, that is the eddy turnover time. So, if L is the length scale and the velocity is u, okay, so L by u gives us the time scale which is called the eddy turnover scale, okay, and u square is basically the energy that is carried by that eddy. Now, so this is the energy at the largest eddy level, right. Now, for the smallest eddies we said that dissipation is important. Dissipation is important. What is dissipation? Dissipation takes place where viscous stresses are actually the most important parameter. So, if dissipation is taken as epsilon, okay, it is given as, okay. So, this is written in the index notation, where Sij is basically given as half okay. So, this basically is basically nothing but the cross derivatives, or basically ui differentiated with respect to xj, okay. So, the contraction happens over I and j. So, this is basically what we call the dissipative scale or the dissipation level, right. Now, this will scale, from our scaling arguments we can say that the dissipation will scale something like, okay, because it is Sij. So, basically this is V by neta, where x, if you remember, this is the smallest eddy scale, okay. So, neta is the smallest eddy scale and V is the corresponding velocity, okay. So, in other words, we know that since there is no energy accumulation, so whatever energy is possessed by the larger eddies has to be pumped into the smallest eddies where they are actually dissipated. So, basically this translates to that your u cube by L has to be the same as your gamma v square by neta square, right. So, in other words, the energy per unit mass of the largest eddies has to match whatever is the dissipation level, right. Okay. And so, this is the first important relationship that we have, let us call this 1. Okay. The other important relationship is that V neta by gamma should be of the order 1 at the smallest eddy scale, because here this means here the Reynolds number, this is basically nothing but the Reynolds number. Reynolds number is of the order 1, okay. when Reynolds number is of the order 1, because it is a ratio of inertia versus the viscous stresses, right. When it is of the order 1, that means your viscosity is important, right. When neta is of the order of L, right, in that particular case your Reynolds number is say 1000, 3000, whatever it is, right. So, in that case the inertia is much more dominant than the viscous stress. Okay. So, these are the two relationships that you get, this is 2. Now, what we can do is that, okay, we can get rid of the scales, okay, and we define our normal Reynolds number as UL by gamma. So, this is the Reynolds number based on the largest scale. In most of the cases, if you recall the example that the eddies are shed, okay, behind a sphere, then this L will be of the order of the size of the sphere, okay, because the largest eddies are always of the size of the obstacle in this particular case. Okay. So, if you take these two situations into consideration, from one equation you will get your neta will be equal to or scales as L Reynolds number to the power of -3/4. The other one will be V will be U Reynolds number to the power of -1/4. So, these two corresponds to the smallest eddies, these basically correspond to the largest eddies, as simple as that. Okay. So, in other words, your neta by L basically scales as Reynolds number, you can write it L if you want, it is 3/4. Okay. In other words, the ratio of the two scales, this is the smallest and this is the largest, right, is actually proportional to Reynolds number raised to the power of -1/4, or in other words, as the Reynolds number increases, okay, the difference between these two scales actually widens, right. Okay. So, if you are dealing with say for example Reynolds number equal to 100 or 300, okay, you will have a scale difference. As you go on increasing the Reynolds number, that means this fraction is becoming smaller and smaller in nature. It would mean that neta will be a smaller and smaller fraction of L. So, this essentially implies that since neta is becoming a smaller and smaller fraction of L, the disparity between the two length scales, that means from between this and this, right, this is of the order L, this is of the order neta, this disparity actually goes on increasing. So, between the largest scale and the smallest scale, the disparity increases as you go on increasing the Reynolds number, okay, and this poses one of the most serious problems in turbulence modeling, right. So, as Reynolds number increases, okay, neta and neta by L ratio decreases. Okay. So, for example, if you take Reynolds number equal to 1000, okay, say as a sample case, L is of the order of 1 centimeter, then you will have neta which is of the order of 0.05 millimeter, or in other words 50 microns. Okay. So, for a 1000 Reynolds number case, 1 centimeter is the largest eddy, okay, whereas 50 microns is the smallest eddy. Okay. So, this poses a very serious problem if you want to do say for example turbulence modeling, right, because in that particular case, say if your Reynolds number is of the order of 10 to the power of 5 highly turbulent flow, right, you can calculate, okay, that if your L is of the order of 1 meter, right, what will be the value of your neta from this particular expression. It is very easy to calculate, right. You will find that the disparity between these two scales is so huge, that means your grid, if you are trying to basically discretize this whole thing and do a CFD, okay, of the whole problem, you will find there is one and only one important bottleneck here, and that bottleneck is that your grid size has to be very small. So, not only it has to resolve the neta scale, because that is where dissipation is important, at the same time you have to resolve the largest scale which may be of the order of 1 meter. Okay. So, even for very simple flows, this is a very taxing process. Like for example, if you do a simple flow through a pipe or a jet that is coming out, okay, this is a very taxing process to begin with, right. Okay. and more the higher the Reynolds number and more complicated the flow is, okay, this creates a insurmountable problem, okay, in CFD. Okay. Sometimes if you with the best of the supercomputers available, it can take years, okay, years actually to solve physically, you know, a realistic level problem. Say flow through a gas turbine is one of the realistic level problems, right. On the top of that, if you have a chemically reacting flow, that means there is combustion and things like that going on, that happens at the molecular scale, right. So in order to resolve that, you further need to have that kind of resolution, right. So the idea of turbulence is as follows, okay, before we take on the next dive, okay, that Navier-Stokes equation still governs the turbulence, okay. Let us be clear about that. It still governs turbulence, okay. The main problem is that the sensitivity to initial condition and boundary condition is one of the prime, as we already narrated, one of the prime factors, right, because of the sensitivity, okay, because of the nonlinearity of the Navier-Stokes equation, anything gets amplified, and turbulence is basically a manifestation of that, okay. Now on the other side, this disparity of the length scales, that means you have too many, a whole region maybe from 50 micron all the way up to 1 centimeter or 1 meter, basically this is the range that you need to cover. That means you not only have to see what is the dynamics of the large eddies, you have to also see the dynamics of the smaller eddies, right. So all these things needs to be done in a computational framework, okay, because analytically it is not solvable. Okay, that is very hard to do, but people do something called direct numerical simulation, which is called DNS, and there are other things that people do, but that is for very simplistic level problems to understand certain things, okay. But other than that, okay, one has to devise some kind of a framework, okay, through which you can address this turbulence, because it is a very time consuming affair, okay. And if you are working in industries or you are trying to solve any engineering problems, you need answers. You cannot wait for years for a simulation to complete. That can be long term, but at least you need for quick design fixes and things like that, you need to know that what can be done with this Navier-Stokes equation. Maybe a simpler version can be used, okay, to understand turbulence. So Navier-Stokes equation as such is not unclosed. So when you hear people saying that a closure problem in turbulence is one of the main factors, okay, that closure problem is actually created by us, okay. Normally the Navier-Stokes equation is not unclosed, okay, it is exactly the same. It is like that when we try to extract certain statistics or we try to do some simplifications to the Navier-Stokes equation, that is where we initiate certain things, okay, which we will see in due course, that what are those certain things that happens, okay. So turbulence, another thing that we should like to mention over here is as follows, and this is also important. So if you take a jet, say coming out of a pipe, okay, so it can be the tailpipe of your engine, say for example. So the flow is turbulent, okay, and you take one point over here, another point over there, right, separated by a certain distance. So what do you expect to see? Okay, you expect to see that if this point 1 and 2 are basically close to each other, okay, you will find that when there is a vortex that is being shed, when there is a eddy turnover over here, okay, that would have some effect in 2 as well if they are very close to each other, okay. But as 1 and 2 get separated from each other, okay, that means as their separation increases, you will find that the effect slowly becomes gradually nullified, okay. So typically we address these problems, we will do that later, what we call the 2-point correlation kind of a technique, that how if you create a disturbance here, how is it correlated with a nearby point. So this can be done as a spatial correlation, this can be done over temporal correlation, so all kinds of things can be done. Or in other words, so you have an eddy that is being shed depending on the level of turbulence, okay, that effect of that eddy somehow will be felt at 2 as well. So if you measure the velocity profile at 1 and you measure the velocity profile at 2, you will find that there will be a degree of correlation between the two, right. And this correlation does not really happen with respect to one component of the velocity. Say for example, you are measuring u prime, right. So, u prime you are measuring at one particular point and then you are measuring u prime at some other point, say x plus r, this may be x, right. Okay. So, you are measuring u prime at two particular locations. Okay. Similarly, so this is one component of the velocity disturbance has created a fluctuation in a nearby field. Okay. Similarly, you will have like a v prime at x can actually cause a u prime at x plus r. Okay. So, basically you can have a parcel of fluid which quickly goes from one point to the other. It will not only cause a variation in the u prime, but also in the v prime. Okay. So, that is the whole idea. So, all these components in turbulence is highly 3D in nature. Okay. Turbulence is highly 3D. So, it is so that is one of the basic concepts. So, you can have a lot of statistical techniques, some of which we will try to see given the interest of time, but but one important factor will be for a turbulent researcher is to find out how good the correlation is, where the flows are basically correlated to each other. Okay. So, but those are statistical techniques that will come a little later, but keep in mind that when you have a fluctuation in the x component of the velocity, you do have a fluctuation in the y component of the velocity as well. So, you cannot take those terms to be equal to 0, and that is exactly paves the way for some of the closure problems that we are going to have very shortly. Okay. So, we are going to introduce what we call something called the Reynolds averaged Navier-Stokes equation, but as we said, the turbulence is kind of a, it has got some statistical origin and things like that. We always say things like this. Okay. So, let us look at what is Reynolds averaged Navier-Stokes equation before we go to the turbulent boundary layer. So, it is called Reynolds averaging. Okay. So, Reynolds averaging means that you have a u which has got a u bar and you have a u prime. So, basically you are dividing the terms into two terms basically. One is a mean component and we will see what the mean is, and one is a fluctuating component, right. Okay. Similarly, all quantities will behave like that. So, p will have a p bar plus p prime, sorry. Okay. V will have a v bar plus v prime. W, as I said, turbulent is highly 3D, and even if we have temperature, T will have a T prime, right. Okay. Now, here your u bar is basically summed over, this T is not the temperature, this is basically the time averaging. It is done over a long enough time period. Okay. It is done over a long time period, so that you basically smother out everything. Similarly, your u prime, if you take an average of u prime 0 to t u prime dt, that should be equal to 0 because it is random fluctuations. So, if you average a random fluctuating quantity over time, this will be equal to 0, right. So, u prime, that is just the fluctuation, right. U prime is what? U prime is basically u minus u bar, right. So, average of that, if you take an average of that particular quantity, this should be equal to 0, right. Okay. So, let us establish certain rules based on this, so which will be needed. So, these are the rules. U plus v bar, so the average of the summation of two quantities is basically u bar plus v bar. Okay. U bar by u prime bar, that means is a multiplication of u prime and u prime bar, right, that is equal to 0, right. U v bar, okay, that is equal to u bar v bar plus u prime v prime bar, this is not equal to 0. Okay. So, u prime v prime bar. Okay. Similarly, u square bar is given as u bar square plus u prime square bar, this is also not equal to 0. Okay. So, basically the product of the two average of the product of the two fluctuations is not equal to 0. Okay. Similarly, du by dx bar given by this. So, these are the rules that we lay down for the current problem. Okay. So, based on these rules, now let us do the first stuff, which is mass conservation. Okay. The mass conservation should be the first customer in the business. Okay. So, what we do is basically you have first you split the quantities, that means it comes out as this. Okay. Okay. Now, if you apply the rule now over here, you see that these are all fluctuating quantities over here. So, naturally they will actually go to 0. So, effectively your mass conservation equation looks exactly the same as your mass conservation equation would look like even if you did not do any averaging. So, it is basically that is what we get, right. So, it is basically the dilatation of the average quantities is basically equal to 0. So, in the case of a laminar flow you did not have those bars over there, but this exactly looks like that. So, there is absolutely no problem. So, if you apply a statistical tool, we have basically applied a statistical averaging to the Navier-Stokes to the governing equations, and we find that the conservation equation behaves in exactly the same way as you would expect in a laminar, because the conservation of a mass equation is basically linear in nature, right. But things gets a little dicey when we actually go to the x momentum equation, and the y momentum will be very similar, okay, and the z momentum will be similar as well, right. So, what you have, if you write it in the conservative way, so this is the equation. Now, what we do, first you split the quantities, right. So, you have your du bar by dt plus, and then you take the average. So, it is u square bar plus 2 u prime plus u prime square, you take the average plus d by dy u bar v bar u bar v bar plus v bar u bar plus u prime v prime. You take the average of that plus dz u bar w bar okay. This is equal to minus 1 over rho d by dx p bar plus p prime. Once again you take the average of this plus you take the average of that. Okay. Now, what will happen? Several of these terms will basically knock themselves out. These terms will all go, correct. Okay. So, and this term also, and all these components will go, right, because these are all fluctuating quantities. It has got no prefactors. So, ultimately the equation will be u bar du bar dx plus v bar du bar dy plus w bar du bar dz and dp bar by dx plus gamma minus Okay. So, as you can see, just pay a little bit of an attention to the last, these up to this point it looks exactly like your Navier-Stokes equation, right. Advective term, pressure term, viscous term, right. These three terms that we have accumulated all of a sudden, right, these three terms that we have accumulated, okay, these are basically has evolved because of the reason that the advective terms over here they were nonlinear in nature. Okay. Because they were nonlinear in nature, out pops these three additional terms, right. These additional terms has got its origin in the advection quantity. Okay. They are not of viscous in nature. Okay. They originate from the convection, right. But why we have taken it to the right hand side we will explain in a little bit. But these terms basically we have no idea what they are. One is u prime square bar, one is u prime v prime and one is u prime w prime bar. So, all these correlated quantities like what we said, like how u prime is correlated to itself, right. All these correlated quantities or what is the degree of correlation, we have no idea that how these terms are related to the flow field, what is their nature, right. The rest of the terms we know, right. We know exactly that this is the Navier-Stokes equation, this is what happens, right. So, these terms are basically unclosed in nature, right. They are not closed, and because they are not closed, okay, there lies the problem that when you do apply a statistical averaging to Navier-Stokes equation, because of the nonlinearity you do get this additional popped out terms, right, three terms here. So, each momentum equation will have three terms essentially, okay, but they are symmetric, that is means u prime v prime is the same as v prime u prime. Okay. So, if you put them in a matrix basically you have a symmetric one, right. So, but all these terms are basically unknown and we have to find a way to understand what is the nature of those terms, right. Otherwise, your equation simply becomes unsolvable in nature, right. So, this creates the first of the closure problems. Okay. So, in the next class what we will see that what will happen to the energy equation, okay, because the energy equation will also have similar things that will crop up as a result of this. Okay. So, see you in the next class.